Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, find critical and pseudo-critical edges in a minimum spanning tree. This problem is definitely a hard one, and that's because it involves quite a few algorithms, but it also requires being a little bit clever. So we're given a weighted undirected graph with n vertices, and it's important to note that this graph is connected, so that pretty much guarantees that we will be able to find some spanning tree, therefore we'll be able to find some minimum spanning tree. So that's pretty much guaranteed. And of course, every edge is going to have two nodes that are connecting the edge, but also it's going to have a weight. That's kind of the whole point behind a minimum spanning tree, because in case you don't remember, an MST is basically a subset of edges in this graph which connects all of the nodes together. So for example, one spanning tree could look like this, where you can see all of the nodes are connected. Now we have 5 nodes. How many edges did it take to connect all of them? It took exactly 4. And that's always going to be the case. If we have n nodes, it's going to take n minus 1 edges to connect all of them. And of course, a minimum spanning tree is the spanning tree such that the sum of the weights of all of these edges is minimized. So believe it or not, that's actually the easy part. There are a couple algorithms that can help you find a minimum spanning tree. One's called Prim's, it's similar to Dijkstra's algorithm, and another one is Kruskal's algorithm. This algorithm intuitively is a lot more simple, so this is the one I'm going to be using in this problem. But it's not as easy as just applying this algorithm to this problem. If it was, this would probably be a medium problem, but this is a hard problem for a reason. And by the way, if you're not familiar with these algorithms, I definitely have some videos on them. You can also check out my advanced algorithms course where I cover these in depth. But we'll kind of review Kruskal's algorithm in this video. But I will mention that Kruskal's algorithm also requires union find, which is why it's kind of a pain to code up. But conceptually, Kruskal's is pretty easy. It's a greedy algorithm. We'll be talking about it in a bit. But first, let's finish reading this problem. Our goal is not just to find a minimum spanning tree, but our goal is to find all of the critical edges of the spanning tree. What is a critical edge? Well, in this case, it's defined as being an edge such that if we removed this edge, like we're not allowed to use this edge in our MST, then we try to find an MST without that edge, and what we find is our new MST has a weight that is actually greater than the original weight of the MST. And just to make it a bit more concrete, let me just give you an example. Let's say this is our graph. We have 3 nodes, 1, 2, 3. We have 3 edges. This one has a weight of 1. This has a weight of 3. This has a weight of 4. So what's the minimum spanning tree? Well, it's probably these 2 edges. And how we would know that is using Kruskal's algorithm. We would take all of these edges, put them in a list, sort them by the weight of each edge, in ascending order, because we want to be greedy. We want to choose the edge with the smallest weight first. So we would first pick this edge, and what we would find is by adding this edge, we are introducing 2 nodes to our current tree. And now we would add another edge, and we among these 2, which one do you think we should pick? Well, Kruskal's is going to tell us to pick the one with the smaller weight. And again, we find that we're introducing a new node to our tree. Now, if hypothetically there are going to be cases where we have an edge, but it actually does not introduce a new node, and those edges we would skip. That's not really the case in this simplified example, but it could be the case, and that's why I would recommend really understanding Kruskal's algorithm before getting into this problem. But so far, we found this is our minimum spanning tree. Now, if we try to add this edge, even though we have 3 nodes and we have 2 edges, at that point, we pretty much know that we're done finding our minimum spanning tree. But hypothetically, if we try to add this edge, what we find is that it doesn't introduce any new nodes to our tree. Like we already have these 2 nodes as a part of the connected component that forms our minimum spanning tree. So we found that these 2 edges add up to a weight of 4. That's the weight of the minimum spanning tree of this graph. Now, what if I took this edge and told you you're not allowed to use it? I removed this edge. Well, then the new minimum spanning tree is going to look like this, and the weight of it is going to be 7. So that is what makes this edge a critical edge, because now we can't create the same minimum spanning tree with the same original weight. So algorithmically, how can we find if an edge is critical? Well, it's actually pretty simple with Kruskal's algorithm, and it pretty much is the brute force way. So actually, there's not a lot of cleverness involved in finding the critical edges. What we're going to do is basically run Kruskal's algorithm once on this graph, just like I did. We're going to find that the weight of the minimum spanning tree is 4. Okay, then we're going to try one by one. Let's try finding the MST without this edge. And in this case, we got a weight of 7. Therefore, we know this is critical. Okay, now let's try finding the MST without this edge. And once again, we're going to have a minimum spanning tree that looks like this now, and the weight is going to be 5. So once again, it's greater than the original MST weight of 4. So once again, this edge is critical. So we found 2 critical edges so far. Now let's try it with this one. Well, now we can still form the original MST, so therefore this edge actually is not critical. So it's pretty easy to find the critical edges. But what about the pseudo critical edges? Well, let's first read the definition for these. An edge is pseudo-critical if it appears in some minimum spanning trees, but not all of them. So kind of by definition, if an edge is critical, there's no way it's going to be pseudo-critical, right? Because a critical edge has to appear in all of the minimum spanning trees. Because as we know, a graph can have multiple minimum spanning trees. Not in this example, actually, but let me kind of make another really simplified example like this one. Let's suppose that all of the edges have a weight of 2. Then, well, this is kind of a minimum spanning tree. This is one valid minimum spanning tree. And also, this is a minimum spanning tree as well. There's potentially many minimum spanning trees for a single graph. Now, in this example, that's not the case, but it definitely could be the case in other graphs. So that's just to help you understand the definition of a pseudo-critical edge. It could appear in some minimum spanning trees, but not all of them. A naive way to find pseudo-critical edges would be, well, just take all of the edges, all of them, and then remove the critical edges. Isn't it just that easy? Can't we just take every non-critical edge and then say it's pseudo-critical? Unfortunately, we can't do it. It's not that simple, because it's actually possible that some nodes or some edges like this one actually never appear in any of the minimum spanning trees, because in this case, there's only one valid minimum spanning tree, and that's this one. This guy never appears in the minimum spanning tree. Therefore, this is not a critical edge, and it's also not a pseudo-critical edge. So then how do we find the pseudo-critical edges? Well, like I said, we know that a critical edge can never be a pseudo-critical edge. So as we're looping and as we're checking, is this edge critical? If we find that yes, it is critical, then we continue. But if we found that this edge is not critical, then we would want to test, well, is this node pseudo-critical? Well, how can we test that? How do we know if this is a pseudo-critical edge once we've confirmed it's not a critical edge? Well, it would be by taking this edge and including it in the tree. We're definitely including this edge. We're forcing ourselves to include this edge, and now we're checking, is it possible for us to find a minimum spanning tree with the same weight as the original? Again, this example is not the best for this one, because we know that this was a critical edge, but that's the idea. If we find that by forcibly including an edge, we can create a minimum spanning tree, that must mean that that edge was pseudo-critical. So that's kind of the intuition behind this problem. I could spend all day dry running it, but I'd rather just code it up because it'll probably make a lot more sense. And we'll also touch on the time complexity then as well. So now let's code it up, and the way this problem is written, we're returning a list of the critical edges and pseudo-critical edges, but the way we're defining those is by using the original index of each edge. So even though we're going to be sorting the edges for Kruskal's algorithm, we also want to preserve the original index. So the easiest way to do that, in my opinion, is just to iterate over each edge. And in Python, you can do that with enumerate. So enumerating the edges, we get the index, but also the edge at the same time. And the reason that's helpful is because for each edge, let's just append the index to it, because we know that originally each edge was the vertex 1. That's what I mean by v1, and vertex 2 or node 2. And after that, it was the weight. So the edge is connecting these two vertices, and it has a weight of this. And now we're adding the original index to that as well. And we're doing that because now we're going to take the edges and we're going to sort them. But which of these 4 keys are we going to use to sort? Well, in Python, we can specify the key, and I'm going to pass in an inline function, aka a lambda function, which is going to take a parameter. I'm going to call it x, I could call it v, I could call it e. Let's just call it e because it's more descriptive. So for each edge, we're sorting it by the weight. So when we take the index, we're going to take the value at index 2. And this I is actually the original index, so let's keep track of that. So now's the part where we want to find that minimum spanning tree so that we can get the minimum spanning tree weight. But to do that, we need union find, as I mentioned earlier. Now, for me, it's pretty easy to implement union find. I can do it in like 3 minutes probably, just because I've done it so many times. I don't even think about it. I just kind of do it based off of memory. But if you're new to union find, I definitely have some videos on it, and it's also a part of the advanced algorithms course on Leetcode.io. Union find will allow us to determine if 2 nodes are a part of the same connected component. And in our constructor, we're going to pass the number of components we have, n, aka the number of nodes. And for each node, we want to keep track of its parent. Originally, we'll say the parent for each node is just going to be itself. So I'm going to say for I in range n, this is list comprehension in Python. We're basically creating an array from 0 to n minus 1. And also for each node, we want the rank of it, aka the size. And initially, we'll say that is going to be 1 for each of them. So 1 times n here is going to create an array of size n filled with ones. And there's 2 main methods you want in your union find, and that is find, and the other one is called union. So find is going to be given a node or a vertex, so v1 in this case, and it's going to find the parent or the root parent of v1. And I do that usually with a loop. A lot of people do it recursively. It doesn't really make a huge difference, I think. But while v1 is not equal to the parent of v1, because we know that a root is going to have no parent, or the parent is going to be itself. That's kind of how we initialize the parents. But if that's not the case, then we continue traversing up the parent chain. And we could just say v1 is going to be equal to its parent. But there's another small little optimization you can make with union find. It's called path compression, where we basically take the parent of the current vertex and set it equal to its parent. So this probably isn't necessary to pass this problem, but it's a small little optimization you can make. And once we do reach the root parent, we can just return that, and that will be stored in v1. Now, second is union, where we take 2 vertexes, v1 and v2, and we try to combine them into a single connected component. In union find, we do that by getting the root parent of each vertex, because that will allow us to know if they're already a part of the same connected component. So we call find on each of these and find their root parents. Now, if their root parents are equal, that means they're already a part of the same connected component. So what we're going to do is return false, because we want to know whether this union was successful or not. That's going to be important for us later on. But if that's not the case, we're going to end up returning true. But before we return true, let's check which one has a larger rank, because an optimization you can make in union is union by rank. We want to take the one that has a larger rank, so we can figure that out like this. So if P1 has a larger rank, then we take P2 and set it as the child of P1, aka we take P2 and say its parent is going to be equal to P1, and then we also update the rank. So in this case, since P1 became the parent, it's still the root, and then we can take its rank and add the rank of P2 to this one. I know this is kind of confusing if you don't know anything about union find. It's not something you're just going to come up with, and it's definitely something I would recommend understanding before you try to tackle this problem. I have a lot of resources on this. Now, if the opposite is the case, maybe this one had a larger rank, we're just going to add an else here. And this is the part where I just turn my brain off. I just copy and paste this and just swap the variables around. Whoops. And then take this. This is P1. This is going to be P2. This is going to be P2. And this is going to be P1. Okay, cool. We have our union find done. I'm not really going to be talking much about this anymore. But one thing I'll quickly say is, how would we know if we took all of these vertices or nodes and connected them into a single connected component? Well, the easiest way to know would be if one of the ranks of these, like one of these ranks is equal to n, because that means one of the components has all of the nodes a part of it. And we're actually going to be using that fact later on down here, because that's how we're kind of going to know if we found a minimum spanning tree or not, at least for one of the cases. For the basic case here, now we can actually construct a union find component. I'm going to call the union find constructor, passing in n, because that's how many nodes we have. And now I'm going to just start iterating through our edges that we sorted up above. So we're going to unpack the vertices and the weight and the index by iterating over the edges like this. And we're going to call union on these two vertices, V1 and V2. And if this returns true, that means the union was successful. And in that case, we can take our minimum spanning tree weight and increment it by the weight of this edge that we are currently iterating through right now. So by the end of this loop, you might be thinking, how do we know for sure that we actually formed a minimum spanning tree? Like I mentioned, how do we know that all of the nodes are now a part of a single component? Well, first of all, we know for sure that the given graph is a connected graph. So by the time we reach the end of this, we know for sure the graph is going to be connected. And we also know it's going to be a minimum spanning tree because our union operation is not going to execute every single time. If we have two vertices that are already a part of the same component, this is just not going to execute. Therefore, it's not going to return true is what I meant to say. And therefore, the weight is not going to be updated. It's not going to be incremented. So that's why we don't have to do any special check here. By the time this is done, this will be the minimum spanning tree weight. This is the true minimum spanning tree weight. Now, our job is to find the critical and pseudo-critical edges, and we're going to store those in two lists. And this is the part where I'm kind of just going to brute force this. I'm going to go through every single edge, and I'm going to do that with unpacking, just like we kind of did up above, N1, N2, that's going to be vertice 1, vertice 2, pretty much, and the edge weight and the index in edges. And the reason I'm getting this index from the edges, and I'm not just saying for I in range, like length of edges, because that would not give us the original index. Remember, we did that work up above for a reason. We wanted to preserve the original index, because we need that when we're building the output. When we're building these two lists, what we're going to add to them is the original index of each edge. So that's very important. I actually didn't do that when I first solved this problem, and I was wondering, where did I go wrong? But now we're going to do two things. We're going to try to find the minimum spanning tree without the current edge, just like I mentioned earlier. Because if we can't create the minimum spanning tree without this edge, that means this edge is a critical edge. So let's do that. And we're actually going to do something very similar to what we did up here. So I'm literally going to copy and paste this code. And before I copy and paste it, I'm going to say the weight currently of the MST that we're trying to build. I'm going to create the same union find with the same name. You can do that in Python because now I'm constructing a new object because we're never going to need this one ever again. But if I wanted to, I could rename this to something else. It's not a huge deal. But as we iterate through each edge, we want to skip the current edge. How do we do that here? Well, the easiest way is just to say if I, which is the index of the current edge, is not equal to the index of the edge that we're iterating through right now, which is also I, that's a problem. I'm actually going to change it to j. So here we're checking if I is not equal to j and the union find operation is successful, then update the weight, not the MST weight, just the weight that we declared up here. Okay, we're getting close to the end of the problem, so just bear with me. I know this is definitely a long one. That's why it's a hard. But now we want to know, did we form an MST or not? One thing to check would be, is the weight greater than the MST weight? Because if this is the case, that means this edge was critical. That means without this edge, we were not able to get the original MST weight. And if that's the case, what we're going to do is to our critical edges, we're going to append the index I of this edge. But this is actually not enough. Perhaps without this edge, we weren't able to actually create a tree like at all. Maybe we were just not able to connect all of the nodes. How would we know that that's the case? Well, we would check in our union find dot rank array, what is the max value in the rank array? It should be equal to n, but if it's not equal to n, and it's probably less than n, then we did not find our MST. So if either of these two is true, either we don't have enough nodes to create like a connected graph, or our weight was too large, then we did not find the MST. Therefore, this edge is a critical one, and we're going to add it here. Now, I'm also going to add a continue statement if that was the case, because we don't want to execute this part if we found a critical edge. Because now we're going to try with the current edge. We're forcing the current edge in the MST in our like connected component. And we're doing that. The reason we have a continue here is because remember, a critical edge is definitely not going to be a pseudo critical edge. But here we're going to do pretty much the same thing up above. If here we create an MST that has the same weight as the original MST, that means this edge is a pseudo-critical edge because it's a part of some MSTs, but it's not a part of every MST like the critical edge. So here we're going to be forcing this node in. So first I'm going to create a union find component, a union find instance, just like this. I'm going to set the weight here actually equal to this weight, E weight, because we're forcibly including this edge, so we can initialize the weight as the same thing. And we should probably also call union find.union on these two vertices because we're forcing them into our minimum spanning tree. Now, I'm actually just going to copy and paste this up above as well because we're going to be iterating through all the edges. We don't need this part of the code actually, because if we tried to take this union and call it again here, it just wouldn't execute. It would just return false, remember? Because if we try to add two nodes that are already a part of the same connected component, it's going to return false. Therefore, this wouldn't execute. So we don't even need to check the indexes like that. Now, by the end of this unioning part, like at the end of this Kruskal's algorithm, how do we know if our minimum spanning tree has the same weight as the original minimum spanning tree? Well, that's pretty easy to check. If we just check if weight is equal to MST weight, then we can take pseudo and append to it index I. You might think, shouldn't we also check that the rank is the same? You might think, shouldn't we also check that we were able to create a connected component? Well, we know for sure we're able to create a minimum spanning tree. Like, that's guaranteed. And down here, we actually didn't have any restrictions. All we said was we're forcibly including this edge. It's not like we're not allowed to include any of the other edges. Therefore, we're guaranteed to be able to form a minimum spanning tree. The only thing we need to check is, does the weight match the original? And if it does, then we append like this. Now, after everything is said and done, what we actually return out here is going to be an array with two subarrays, the critical edges and the pseudo-critical edges. So that's the entire code. It's definitely quite a lot of code, and it doesn't even fit on one screen. But now let me run it to make sure that it works. And as you can see on the left, yes, it does, and it's pretty efficient. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. Thanks for watching, and I'll see you soon.